Hi everyone, I'm Alex Hansen, and in this video we're going to look at linear regulators, which we will later distinguish from switching regulators, which is what we'll spend the majority of this curriculum talking about. And we'll see that linear regulators are better than, for example, resistor dividers at producing a regulated output voltage, and they can produce a very clean output voltage, which we'll see later is quite different from the switching regulators that we'll spend most of our time on. We'll talk about the concept of dropout voltage, and we'll learn why linear regulators are often called LDOs. And we'll see that linear regulators are horribly inefficient, and there's also some other things that they can't do, which means they're not the ideal choice for most applications. Nevertheless, they do still come in handy. Finally, we'll make a note that the control loop of an LDO, in order to be stable, usually requires some amount of output capacitance. And for some LDOs, the choice of capacitor can be particularly important. I'd like to motivate the LDO by drawing the following circuit. This is a resistor divider circuit with R1 and R2 coming from an input voltage and producing an output voltage. And of course we know that if we choose these resistors properly, we can make the output voltage, which is equal to R2 over R1 plus R2 times V in. We can make the output voltage whatever we need for it to be. The problem with doing this kind of voltage conversion in a power converter is that, kind of by definition, we want to deliver a certain amount of power to our load. So if I go ahead and draw a load in here, this load may be a current source or a resistor or some other complicated impedance. I'll just draw it as a current source though. This is my load. And hopefully you can see that as I draw more current in my load, the output voltage will decrease. And this is because, in addition to having current flowing through R2, I now have a lot of current being pulled through the load. And all of this current flows through R1. Therefore, the voltage drop on R1 will increase, and I expect the output voltage to decrease. So I can demonstrate this in a cartoon as follows. So you can see that with fixed resistors, it's hard to deliver just the right amount of power to a load at just the right voltage, and it's impossible to do so if the load is varying. The solution, of course, to this is to have one or more of your resistors be variable. So if, for example, my top resistor becomes a variable resistor, R1 and R2, then no matter what load I hang off of this, I can always adjust R1 to be whatever it needs to be to make sure that the output voltage stays at its target value. This is exactly the concept behind a linear regulator. And in practice, the way we implement this is with a transistor. So for example, I might choose to use a PNP transistor in bipolar, or a P-channel MOSFET in a CMOS process. And at a certain point, if I have a variable resistor or a transistor that's operating as a variable resistor, I don't even necessarily need the R2. And I can simply hook up my load directly to the transistor. And if I add some control circuit, for example, something that measures the output voltage and puts out a control signal, and that control signal ultimately is the gate voltage of the MOSFET, then by controlling the gate voltage of the MOSFET, I can make the equivalent resistance of the transistor or in other words, the voltage drop across the transistor, just exactly the right value no matter what the load is. And so this part in red, including the transistor itself and the control and the sensing, is what we would call a linear regulator. And you can see that at its fundamental level, a linear regulator is a three-terminal device. It has an input voltage connection, it has an output voltage connection, and it has a ground. Now, there are three behaviors we need to review that are important when it comes to linear regulators. The first is efficiency. This is actually really easy to calculate. The efficiency is just V out times I out. This is the power delivered to the load, divided by V in I in. This is the power that comes from the source. Power to the load over power to the source is efficiency. And hopefully we can see that the input current, I in, and the output current, the current going to the load, I out, are in fact the same. So I in and I out are the same as each other, and so efficiency is just equal to the output voltage over the input voltage. And these numbers aren't numbers you get to choose, right? You have a certain input voltage available, you must deliver a certain output voltage based on the load requirements, and so this is absolutely fixed. Now, of course, a linear regulator can consume more energy than that. In particular, the control will consume some energy, and so the efficiency is technically less than or equal to V out over V in. To make this more concrete, let's consider stepping down 12 volts to 5 volts. The efficiency in this case is 42%, which is horrible. Similarly, if we were to step 5 volts down to 1 volt, this would be another common conversion. This has an efficiency of 20%, which is even worse. And even a step that's not so bad, right? 5 volts down to 3.3 volts, for example, which are two adjacent logic levels, even this step is only 66% efficient. Compare all of these to a typical switching converter. A typical switching converter can easily get efficiencies over 90%. So linear regulators are not very efficient. In fact, they're very inefficient. And even though a linear regulator is a very cheap and easy thing to implement, it's just a transistor and a very basic control circuit, the low efficiency of the LDO means you might have to put a very large heatsink on it, which ruins its size advantage and can ruin its cost advantage as well. So linear regulators are best reserved for very low power applications where the heat doesn't matter very much and where the efficiency doesn't matter very much. The second thing I want to talk about is dropout voltage. The dropout voltage is nothing more than the minimum amount of voltage that has to appear across the device. So if this is VDS across the device, then the dropout voltage is just equal to VDS min, the minimum drain source voltage across the LDO that will still allow it to operate. And this is based on controller parameters and so forth. Most modern linear regulators like to advertise a low dropout voltage. And this is where we get the term LDO from, LDO, low dropout. And you'll hear people talk about these interchangeably. Someone will say linear regulator, someone will say LDO. They're not actually trying to talk about different things, typically. They're just using two very common terms for what in modern times is essentially the same thing. The final concept I want to talk about is stabilization, or stability. And the stability of an LDO comes down to its output capacitor. So if I draw a block diagram of an LDO, and I'll draw my load hanging off the end here, the stability of the LDO depends on how much capacitance and what kind of capacitance is connected to the output here. Now, it's typical to put a capacitor at the output of any kind of power converter in case, for example, the load suddenly changes to a different value. You don't want the voltage to drop, and so you have this source of high-frequency current available in the form of the capacitor. So that's common anyway. The trick with LDOs is that they sometimes have a minimum capacitance, otherwise they won't even be stable. In other words, the output voltage won't even settle to the value you want it to settle to. Sometimes they have a maximum capacitance. I've seen that before. So if you have too much capacitance hanging off that node, you can actually make the LDO unstable. This can be particularly tricky because sometimes your load is an integrated circuit, and you may have hung some bypass capacitance across the power pins of your integrated circuit. And if you've got a whole bunch of those, there could be a lot of capacitance. And so you may accidentally cause your LDO to become unstable. Another feature that's very tricky is sometimes these capacitors are required to have a min and a maximum ESR. So the ESR is important. Now it makes sense that you would have a maximum ESR, right? If you have too much ESR, then the capacitor doesn't really look like a capacitor anymore, it looks like a resistor. But the minimum ESR can actually throw people for a loop sometimes, and in fact I've fallen for this myself. Some linear regulators' control loops are actually stabilized by assuming a certain amount of ESR and taking advantage of the zero associated in that control loop. And we don't have time in this video to go over all the little details of it, but it's something to be aware of, that some LDOs actually want the capacitor to have a reasonable amount of ESR, in which case you might use a tantalum capacitor instead of a ceramic. My solution to this problem? Simply look for linear regulators that explicitly say in the datasheet, stable with ceramic capacitors. Many modern linear regulators are like this, but I always look for a phrase like this when I try to use LDOs. It just makes your life a lot easier. So we've seen that linear regulators can provide stable output voltages. They have a feedback control loop, and so they can keep the output voltage where it needs to be. Because the linear regulator is linear, there isn't a lot of noise at the output, which is useful in some applications. We learned about dropout voltage and low dropout regulators, and we also saw that some LDOs have a very specific capacitance requirement, both on the capacitance and the capacitor ESR, in order to form a stable control loop. Finally, we emphasized that linear regulators are very inefficient, especially when the voltage conversion ratio is large. This is a major motivation for moving to switching regulators, which we'll introduce in another video and we'll spend pretty much all of this curriculum talking about.